No, because that is not a tert-butyl group. And it can't be tert butoxide, which is TBUO minus, because according to our table, anything that's a weak-base weak nucleophile has to be protonated. It has to be ROH, not RO minus. Well, here's the deal. You know that the bromine got substituted, correct? And you know it got substituted by an oxygen bonded to an isopropyl group. So I have two options. I make it isopropoxide and I put O minus, or I put isopropyl alcohol and I put OH. What's the best option here? Given the fact that this gave me a carbocation intermediate with two different stereocenters. What I mean to say there is, the fact that I have two different stereocenters is evidence of SN1. So I need an oxygen-based reagent that will give me SN1. Will O minus give me SN1? RO minus is here, never does SN1. I need an oxygen agent, no, here, that prefers SN1. So I need this to have an H. Just like over here, we used ethanol to give us E1. If you gave me O minus, half points off. You knew the carbon chain that needed to be there, but you didn't recognize the difference between the alkoxide strong nucleophile and the alcohol weak nucleophile that prefers SN1. Anything else that I need to specify with my reagent? Low temp. I don't want the elimination product. How many Zaitsev elimination products are there? If this reaction did eliminate, up here, if this reaction went through E1, how many Zaitsev products could be formed? It could form an alkene here, which is di-substituted, or it could form an alkene here, which is di-substituted, and structurally different. So there are two Zaitsev elimination products. Neither is more substituted than the other. They're both equally stable. That should remind you of back when we were learning about alkenes, and you had to do those active problems that said, given this alkene, what alkyl halide starting material could be used to make it? Or how many different alkenes can be made from this alkyl halide starting material? All right, I think I lost a couple of you there. I just want to show you, if you did do heat here, you get two structurally different alkenes that could form. Equally stable, structurally different. Both are di-substituted. Anybody have reagents for me on the bottom one? Middle one, I mean. We know there needs to be heat. Does it matter whether I use chloride, water, or alcohol? It needs to be an alcohol? Why? Well, I'm eliminating at a secondary, oh no, I'm sorry. I'm eliminating at a tertiary alkyl halide. And because we're in the category of SN1E1, I want you guys to be thinking about these weak bases, poor nucleophiles. Doesn't matter what it is. It could be chloride, it could be water, it could be any alcohol. There's no wrong answer so long as you provide heat. Water, alcohol, chloride, all give the same product. Are you okay with that? There's no substitution, so it really doesn't matter what I add. Down here, I substitute my tosylate for OH wedged, OH dashed, and I form a diene. What do I need? Here there's one answer. I need water. The way to make an alcohol is to use water. Water is the precursor to alcohol. Do I add heat? Do I add low temp? No, because I'm looking to get all of those different combinations. Yvonne, what could I change if I wanted to isolate this? No? New? What could I add to my reagent if I wanted to isolate this diene? Heat. Add water and heat, or alcohol and heat, and it will drive the elimination reaction. This was the hard part. The rest of it, much easier. Why don't we take a quick break? 5 minutes, and we'll be back at quarter after. We'll look at SN2 and E2, and then the mechanisms. Thanks for coming. I started a new one. Yeah. Review days next week. So if you can make it, come with questions. See ya. Yeah. We just had the director of ADS come in back with the Synod on Monday. And people were like airing a bunch of grievances about how hard it is and how it used to be the initiative of the student to have to set up for the final exam, or for the exams to be proctored, and now it's the initiative of the professors. And some professors are like, that's too hard. Others are like, I do it anyways because I think about my students. I didn't like know how to formulate this, but I wish that I could set up for you to go and schedule a time, and then for me later to go in and add the document. But as it is, if I set up the ability for you to go and do it, which I don't mind doing, it's not that hard for me to do. If I set up for you to be able to go and schedule a time, I have to submit the file with it. So I can't really go in and submit until I have the exam ready. There's some other alternatives we could consider, which is you could come in 2 hours early. If I have this, if I can have this room, then you could come in 2 hours early, and I would probably offer this as holiday accommodation to students. But then there's that issue of like when other people start coming in, and then getting them started. That's annoying. Annoying for you as a student taking the test. And a last option would be me proctoring you all on Zoom all together, wherever you are, and then me just facilitating the rest of the class taking it too. Fingers crossed though that you'll be able to find a time at the testing center. The other thing is, I know our testing is Monday night, but since I'm sending it to the testing center, I can't guarantee that you'll be able to do it Monday. So I will offer a.
I was planning for like Monday or Tuesday. I think, like I set those 2 dates to the side just because I'm like, I know it's going to be
Good.
I think Monday's going to be really busy at the testing center. Usually it is the first day of the testing center because all of the people with accommodation do that first day, so they have the rest of the time off.
I really would have expected the opposite.
Everyone wants to get it done. So
I would have thought Thursday would be the busiest day.
well, there's usually Monday and then towards the end.
So like the first day and the last day are the
Yeah.
busiest days. Interesting.
So if they can study.
Yeah, I mean, I totally expect. When I tell my Gen Chem 1 students, you can register from the 15th to the 18th, I totally expect half or more are registering on the 18th. Get as much time as you can to study.
I mean, not as much for 18, so
Yeah, good for you. Have fun. Will, you mentioned just before that this was starting to make sense, how the table reads with this. Could you explain that again?
Wait, what?
You said, I overheard you before, you said, oh, I'm starting to get it. It's just the table.
Yeah, you just match this table to that table. Like, that's what I was saying. Like I was just explaining to them, it's just like you have to look at what column. Well, first we have to look at which row because that's the most important thing. You have to look at which column to see like what you need to pull from the top table.
So find the row first.
Yeah, because like you need to know what substitution you're working with, and then you have to identify what I'm trying to describe what is it.
So let's do a pop quiz. Kira, could you tell me if this is methyl primary, secondary, or tertiary alkyl halide? Take a stab. No? Tertiary? The carbon is bonded to 3 other carbons. So that's your first step. Identify what row you're in, because that will make big impacts on what reactions are even possible. Then, if you know the product, try to figure out, was it SN1, was it SN2, was it E1, was it E2? You can't always tell. There are instances that you don't know whether it was SN1 or SN2. It's impossible to know. There will be times where you can't tell whether it's E1 or E2. That just opens the door for more chemical possibilities. You run down to the lab, you don't have the reagent that you thought was going to do the E2 reaction. Okay, well, it turns out you could get the same product by an E1 reaction, and you've got that chemical. So first identify the alkyl halide because it narrows you down to a specific row. Then figure out what reagent you have and what reactions that predicts, or what reaction has taken place, which is usually evident by some sort of carbocation rearrangement. Let's move on to the second set of reactions, which are SN2 and competition. and I'm going to add in some chemicals. Let's look at cyanide, hydroxide, and tert butoxide. We know that all three of these alkyl halides are secondary alkyl halides. Cyanide is a strong base, strong nucleophile. Nope, sorry. Cyanide is a weak base, but a strong nucleophile, which means that cyanide is expected to only do substitution. Hydroxide is both a strong base and strong nucleophile, which means it will experience competition between SN2 and Zaitsev E2. But tert butoxide is a strong base, poor nucleophile, which means it will only do elimination and T-Zaitsev. So cyanide, only SN2. And we saw earlier that SN2 breaks a bond at the same time that a new bond breaks. There is no carbocation intermediate, so there is no attaching from either direction. You don't get this ability to be R and S. It's only R or S. This should look a bit like the backside attack in the halonium ring from our halogenation reaction. Bromine is wedged, cyanide is dashed. It comes in and substitutes, and it has to do this from a backside attack. So it changes the stereochemistry. Hydroxide will also do a backside attack when it substitutes. So my dashed OH, can't say it right. My dashed chlorine gets substituted at once with a wedged OH. It's a backside attack inversion of stereochemistry, but also we haven't indicated low temperature or heat. So I should predict competition between this SN2 product and this Zaitsev elimination product. Tert butoxide? Yeah, Elliot?
Did I miss here, or do we inverse stereochemistry every time it's SN2?
Correct.
Okay.
SN2, and that's a result of the bond breaking at the same time that the bond is being made. The only way that can happen is if it comes in from the back side, and that means you're swapping the stereochemistry.
So that's why we don't do it for SN1.
SN1 has a carbocation intermediate, and the nucleophile can add from either side, so you get both wedged and dashed. Here you get only the inverse of what you had before.
You basically just answered it, but anytime there's a carbocation, it can be either.
Carbocations, and we actually saw this when we did like random addition, alkene addition reactions. Any carbocation intermediate meant that I could have either configuration of the chiral carbon. And again, just like in the halonium ring, where one halide attacks the halonium ring from the backside and is now added with a different stereochemistry than the halide it just kicked off, this backside attack changes the stereochemistry of the group it just kicked off. Tert butoxide, bad nucleophile, too much steric strain at my secondary carbon, so it wants to do E2. So much steric strain that tert butoxide does not prefer to go to the more substituted carbon and take a hydrogen. Tert butoxide goes to wherever the steric strain is less. That's a less substituted carbon. That's a less stable alkene but less steric strain. Zaitsev E2 elimination with hydroxide, anti-Zaitsev E2 elimination with tert butoxide. These
I
are
was gonna say, if you added to the other side, it's not even a conformational isomer.
structural isomer.
Okay, it's structural.
This is structural, this is structural isomers. All right, so let's do something similar. Oh, let's do, yeah. Can you give me the reagent that's needed to get these different products? Elimination forms alkenes. On this side, they all have one specific answer. I'm sorry. What's going to help you the most is actually this table of the reagents. Where are you going to get it from? Anybody feel brave enough to at least tell me what you want me to put on the board? Really close, but missing one very important thing. She's got it. You've got it. Good. You got the right chemical, but you're missing an important thing about it. N3 is not neutral. Good. How did you know this? And can you be more specific about what is R? Good. That's exactly it. Can you say, rather than R, can you specify what R needs to be? in order to get this product.
We're gonna guarantee it.
Because you notice how your reagent doesn't say H at all? It just needs to be H. Just H. You guys flip back and forth. Bad design.
So just question. Doesn't chlorine refine?
Not necessarily. Can you be more specific about what R needs to be
Oh,
in order to get that
I
specific
think I know what
product?
it needs to be.
Good. Great. Did you overhear what I just said? Oh, no, that's perfect. I thought you just made the change. Yeah. There's only one difference. Yeah. Think about the alkyl halide path and whether the alkene you've made is Zaitsev.
You're right. I
Zaitsev.
forgot about that. Yeah, it does go to less substituted when
Can
you're
you be more specific about what R is in order for me to get this product? Yes.
Yeah, that's right. It has that property. I forgot about that. I think you're right.
This needs to
I think you're right.
No.
It's not.
No.
In my head, I was like, oh, that's gonna be there.
But that makes sense with your logic.
These two positions
If you
that are
don't
being
go to the more substituted,
So
it would.
what I
the
want
bond
is to make sure I don't eliminate.
Yeah.
Remember earlier we said chloride would actually be able to fix this problem. I need something that can go less substituted. All right, guys, we've got a few more things to cover, so I'm going to pull us back in. Wedged bromine to a dash N3. That's an SN2 mechanism. I don't get wedged and dashed. I only get inversion, SN2. The reagent that will give me that N3 is sodium azide, or a lot of you did this totally correct, N3 minus. A number of you put N3, which is not N3 minus, and that negative charge is significant. By the way, sodium azide, kind of cool. It does click chemistry. You can react it with alkynes and make these cyclic structures that it can be really useful in polymer chemistry and medicinal chemistry. But also sodium azide decomposes into nitrogen gas and sodium. And we use that in our airbags to inflate during accidents and give you that cushion. All right. I think the next one that was easiest for you guys was down here. Also SN2 because all I see is inversion. And I need that to be an RS minus group. But if you put RS, you will lose some points because you're not specifying what needs to be there. And in this case, it's an H. So this is SH minus or HS minus. Either way, does not matter. Here, we do not want the Zaitsev alkene. If I used something like hydroxide, methoxide, those would be the most common ones to use. These would give me my most substituted alkene, the Zaitsev alkene. But I want the less substituted possible alkene. That means I want something big and bulky that will only go to the less substituted carbon. And that's why I was saying terp-butoxide is the only right answer there. All right, good work. This, you guys probably noticed, with SN2 and E2, there are less possible answers. With SN1 and E1, you can kind of shuffle through all of them. I also want you to notice, anytime it was SN1 and E1, we were only dealing with weak bases, weak nucleophiles, and this time we spanned across all of the other three categories. So SN2 and E2, a lot more prominent but a lot more specific about the reagent. And I don't want those reagents to be scary. N3 is on your structure, N3 minus is needed to get there. SH is on your structure, SH minus is needed to get there. SCH3, SCH3 minus, right? Also, and this was the problem, I didn't give you guys enough options like this. Let's say that I went from 1-bromobutane and I wanted to get to 1-methoxybutane. Because this is a primary carbon, most things will go through SN2, which means I could put OCH3 minus or methanol. Either one of those would actually work. You'll notice there is no inversion of a stereocenter because there is no stereocenter. There's no backside attack, there's no wedged and dashed, which means my strong nucleophile can do this substitution, and my weak nucleophile can give me the same substitution. It's the fact that I had an ether that told me that I need an alcohol or an alkoxide, because alcohols are the precursor to ethers. Did you guys have questions on this before we finish up with our mechanisms? I want to jump to the second page. Second order substitution, SN2. And E2. Look at the number of steps in these mechanisms. Come on. These are one hump reactions. One activation barrier, one step. These are the simplest mechanisms you'll use, but they are a bit specific. So over the reaction arrow for this first problem, you would likely be given NaCN, or actually maybe KCN. So let's show the mechanism. You have two options when writing KCN into your mechanism. You can ignore the potassium and just write CN, or you can draw the potassium to the side. But if you ever show me this, I will just deduct a small number of points. This does not exist. What does this imply about potassium and cyanide? It implies they're sharing covalent electrons. They do not share electrons. They are ionic compounds. So this doesn't happen. And even when I try to address this, I get a lot of students that will say, okay, I need to show them as ions. I'll show them forming their ions. No, because this doesn't exist. So you have two options. Ignore potassium because it's not playing a role in the chemistry, or write it to the side. But when you see something like KCN, those are ions. They do not have electrons that you need to break. And in the same way, The byproducts that are ionic do not share electrons. For instance, some people will show me things like a reaction where chlorine leaves, and instead of chlorine taking the electrons, chlorine will share them with sodium. No. Sodium is an ion. It does not covalently share electrons with other atoms. So it is chlorine taking electrons for itself, and it will find its way to the sodium eventually. They're in solution. I know I don't show this often, but this is done in a solvent. DMF, DMSO, acetone, water, methanol. There's some solvent that is mediating your reaction. What did you guys use as solvent for the Diels-Alder reaction this week? Or will use this week? Ethyl acetate and Lagroin. Polar aprotic solvent and a non-polar solvent. You always have some solvent mediating this. Okay. So I've drawn potassium, but to be honest, I don't usually draw potassium. I ignore it. It's a spectator. Backside attack. Cyanide bonds to carbon. Chlorine leaves. Done. With E2, we describe the one step as an anti-periplanar beta hydrogen elimination. What we're saying there what's that? Newman projection. Been a long time. Been a long time since we had a Newman projection. Anti-periplanar is saying that the leaving group, let's call that our halogen, should be positioned opposite to the hydrogen on the beta carbon, the adjacent carbon. That is the orientation that they have to be in order to be eliminated. So that means that this leaving group here, which is shown as wedged, what's the opposite of wedge? What is anti to wedged? Dashed. This wedged group can react with this dashed hydrogen or this dashed hydrogen. One of them is Zaitsev. One of them is anti-Zaitsev. Given that we are showing the Zaitsev product, I need to use a Zaitsev base. Let's show something like CH3O-. I could have picked HO-. I could have picked ETO-. I could not have picked tert butoxide. And for our mechanism, there are three arrows that are needed. I need to form a bond between base and acid, break a bond between C and H, form a double bond between C and C, and break a bond between C and OTS. Let's talk about who owns electrons in each of those cases. C to OTS. Who owns those electrons? O or C? O. That means when this bond breaks, it breaks to O. O- and H. O- owns the electrons, so O- gets to share with H. Remember, bonds form from the more negative atom. Who owns the electrons, C or H? C, more electronegative. So carbon takes the electrons from C to H, shares them with its beta carbon who is losing a bond. That's both the breaking of CH and the forming of the CC pi bond. Notice how it goes into the bonding region. We're going to go from a single bond to a double bond. I'll be honest, this is the way that I think of the flow. Base bumps into this molecule and takes a hydrogen. Carbon takes those electrons back and shares them with the other carbon. That pushes off OTS as a leaving group. That's the sequence that I think of those electrons moving in, but it happens all at once. Can you tell me this? Why did the methyl group go from wedged to in plane? It has no more tetrahedral character. This is a tetrahedral carbon. It has wedged and dashed groups. This is a planar carbon. It does not have wedged or dashed groups. So I also take off points when someone gives me a product like this. That doesn't exist. There is no wedge or dashed on a planar alkene carbon. Just in plane. Now it's going to look dashed forever. One step. SN2, one step. E2, one step. Questions on SN1 and E2? SN2 and E2? All right. SN1 and E1, a few more steps, but I want you to recall that some of these steps are familiar. Here's SN1, here's E1. You'll notice that they both start with the same step. The leaving group leaves. To be honest, you don't even need to redraw that structure. You could show that as leaving group leaves, and then we show our next structure. Okay, I'm sorry. I didn't give you a reagent over this arrow yet. Do we know what reagent we need? It needs to have an O, and that O needs to be attached to a CH3. But because this is not a backside attack, you'll notice it went from a wedged bromine to neither wedged nor dashed. That was my way of saying both wedged and dashed. This is not SN2, so it can't be a strong nucleophile. It needs to be a weak nucleophile. That's CH3OH. Weak nucleophile. Step 2 says carbocation rearrangement. Will this carbocation, step 1A says carbocation rearrangement. Will this carbocation rearrange? Secondary carbocation surrounded by secondary carbons. No immediate stability gain. No rearrangement. So we move to a nucleophilic attack. I'm sorry, can you cross out where it says beta hydrogen elimination? BH, I'm sorry, that was my fault. That should not have been on there. Nucleophilic attack. What's my nucleophile? Methanol. The oxygen from methanol shares electrons and attaches to the carbon. Does it attach wedged or dashed? Yes. It adds both wedged and dashed. So I'm going to show that by just drawing an in-plane line. It adds both ways, so I'm showing neither. Are you okay with that? My last step is deprotonation. What base do I have that can deprotonate? I have bromide. It's not a good base, but it's a plausible base given our chemicals. Bromide takes the hydrogen from oxygen and gives electrons back to the oxygen. That gives us our final product. I want you to recognize something. This should feel reminiscent of the halo ether addition. But instead of attacking a halonium ring, the alcohol attacks a carbocation. Nearly the same process, nearly the same steps. Halo ether, halohydrin addition ended with that deprotonation step, just like we see here. Nothing new. There's nothing new here except for the formation of the carbocation. That's it. E1. Here, it wouldn't matter what my reagent is, so I'm going to show CH3OH and heat. But once again, my first step is exactly the same. The leaving group leaves, and I form a carbocation intermediate. Chloride as a byproduct here, and methanol. This time, my carbocation does rearrange. A tertiary hydrogen migrates with its electrons and leaves me with a more substituted carbocation. The last step in this mechanism is a bit like the E2 mechanism, except less arrows. A base needs to deprotonate a hydrogen, and that CH bond forms an alkene. The question is, where should I take a hydrogen from? There's a lot of different places where hydrogens are beta to the carbocation. This should form the most stable alkene. So I need to steal from the most substituted carbon. The other question that you have to answer is, what do you want to be your base? Chloride or methanol? They're honestly about equivalent as bases. Methanol, a little bit more basic. Methanol takes the hydrogen, the CH bond forms a CC double bond. I form my Zaitsev alkene. Plus, I have methyl oxonium chloride. That wasn't so hard. Okay, maybe it's a little bit hard, but is it that much harder than the alkene addition mechanism? No, it's really quite similar. I think the most unique mechanism you're learning here is the elimination mechanism. The elimination is novel. The elimination is unique to this. But the substitution, the deprotonation, boy, it sure looks a lot like things we saw in our alkene addition mechanisms. What gets a little bit more challenging here is simply the diversity of reagents that can be used. There's no one chemical that must be used for a lot of elimination reactions. So there's a lot of correct answers. Okay, two things I want to remind you. SN1E1, they start exactly the same. Part of the reason of why they often compete with each other. SN2E2, they do not look the same, but they are both just one-step mechanisms. They happen at the same time, exactly at the same time. You have a unit test this weekend, opens tomorrow, runs through Sunday night. Monday, we're going to talk about review, Unit 1 through Unit 5. Wednesday, more review, Unit 1 through Unit 5. 2 days of review next week while I work on building your final exam. Come in with questions. Monday morning, I will open up an all unit test question test. All of the questions from all of the unit tests, all the ones you've seen, all the ones you haven't seen. Use it to find the concepts you want to study better. Come in with questions from that, from previous unit tests, from the practice final, the practice midterm, anything that you have. Everything that we covered today and all of the other reactions help you with your final analysis assignment, which I think is due tonight, but you don't have late points for turning it in later. If you get stumped, don't just take a 0 on it. Reach out to me and say, I don't know what functional group to look at. Because look, you could, if you have an alcohol in your compound, you can use that alcohol as a nucleophile. Show me a substitution reaction. If you have a cyanide, you could make that cyanide by a substitution reaction. Show me a substitution reaction. Show me elimination if you have an alkene. Show me addition if you have an alkene. There's a lot of possibilities. So if you feel daunted by that and stuck, just reach out. That is a really good way to apply all of the reactions we've learned and look through your notes to get more accustomed to them before we move into the home stretch of the class. Okay, it's been an honor teaching you this semester. I'm excited for next week where we get to study more and review. Thank you guys for your time. Have a good night.